Thanks, everyone. Thanks for bearing with the normal technical stuff. So we're here to present a tutorial on language modeling. We're going to do quick intros and then kind of go from there. So I'm Nathan Lambert. I'm one of the researchers at the Allen Institute for AI. I'm going to be presenting about post-training. And Kyle and Akshita, do you want to introduce yourself?
Hey, I'm Kyle, researcher at Allen Institute for AI, presenting about pre-training data.
Hi, I'm Akshita, and I work as a research engineer. I will be talking about pre-training.
All right, let's get going. Language modeling, that's what we're talking about today. Let's go forward. So, just as a little primer, this is an area that has seen significant progress. It's not necessarily a super new thing. Actually, the development of these technologies has been built on years and years of research. You can see this timeline in terms of language modeling research, really starting from this idea of self-supervised learning, often supervised text, into development of ideas like fine-tuning, pre-training, switching to generative models, developing new capabilities in these models like in-context learning, realizing scaling laws exist. All of these is really built on this idea that we want open sharing of scientific research. But over years, we've realized that a lot of these developments are happening now behind closed doors, and people don't necessarily have access to study these language models. So really the motivation behind this tutorial is that AI is here today because of practices around open scientific practices, sharing and studying fully open models. But are we basically done? Have we kind of just solved this? Well, not really, and this is why today the goal of this tutorial is to build on some foundational understanding for language model research, try to share this with everybody here today. So roughly the outline for this tutorial, we're going to break this up into data, mostly talking about pre-training data, pre-training, the training algorithms themselves, modeling, and then post-training at the very end. Roughly evenly split across these three topics. We'll have breaks throughout and Q&A at the end. Just a tiny primer. This is going to take like a couple minutes. Language modeling basics. So we're going to assume in this tutorial that you're familiar, comfortable training language models. So terms like learning rate schedulers, batch size, transformers aren't super new. Core language modeling concepts we're hoping you already know. So it shouldn't be a surprise what language modeling objectives are, what tokenization is, what sequence lengths are. And then hopefully there's some snippets of code. They're not runnable necessarily, but they're used for pseudocode for illustration, but hopefully people are familiar with PyTorch. All right, let's assume that you haven't heard about language models, but you've trained models before. Well, language models, or these technologies we have today, look something like this. They take as text as inputs, like a question, and then they're like, let's generate the rest of this thing. And then you toss into a model, and then you get the answer out at the end of it. So text in, text out. And really to understand language models, if you're someone who's done machine learning before, let's kind of open up this input side first. The input side really relies on this idea that you toss your text into a tokenizer that chunks it up, maps these chunks or tokens to token IDs, and then we turn those into embeddings. And now we're in tensor land and everything is good and familiar. So if you want to know language models, well, language models, you have this tokenizer step. That's pretty unique to language technologies. And then you think about your tensors, which have some dimension of batch size by sequence length by some other hidden dimensions. Cool. What about the output side? Well, once you've tossed it to your model and you've done all this matrix multiplication, as everything's very nice, at the end of what you get is you get logits, and they kind of look like this. And then you take some sort of argmax, which gives you back to your token IDs. Then you toss it to your tokenizer, and then you get text again. So again, at the end of this modeling process, you get a tensor of batch size times sequence length times something, and then you rerun your tokenizer and you get it back in. So as long as you're comfortable with thinking about things as eventually everything's in terms of tensor input, tensor output, you should be fine. Otherwise, everything's actually pretty simple, pretty standard. Training actually looks pretty familiar. If you've trained models before, really the thing to pay attention to is the dimension of your tensors. Batch size times sequence length is kind of usually how we think about things. All right. let's get into the nitty-gritty. Hopefully this was a simple enough primer. Data. What is language modeling data? Well, we know it's text, but let's actually open up some of these documents from one of our data sets, and this is what it's looked like in case you've never opened it up before. Data is organized typically hierarchically, so you might have some specification around the source of the data. Oh, this is from Wikipedia. Maybe it's the first version that has been processed because people keep releasing improved versions. You'll have some identifiers for the document, and the core of it is really this. There's a text is just unstructured text and containing all the new lines, weird symbols, etc. In fact, task-specific data, this is with recent developments in language models, task-specific data that have very structured input-output formats also just is represented as text. It's just one giant string. Okay, we have language modeling data. Let's think about this pattern of how do you curate this data. And so I call this the data curation loop, which is you have to do these three things to make any data set. You have to get the data, acquire it. You have to then transform the data in some way, which we call data interventions. And then you validate your intervention by pre-training a language model. And then you evaluate the language model, oh, that's pretty good. And then you transform the data again. You keep redoing this until you end up with your great data set at the end. And maybe per source, so like your GitHub codes, your web crawl data, you repeat this separately for each source. So this section is really focused around these three main curation patterns. I'm going to first talk about what is good data. Then I'm going to talk about how do you get data, how do you transform data, and then how do you make good experimental decisions. And then I have a little summary slide at the end. What is good data? Well, this should come to no surprise to anybody here that you need a lot of it. Good data is data that you can get a lot of. So scale really matters here. We've only seen improved performance of models as a result of scale. What's a newer idea is maybe to machine learning is this idea of quality and really grappling with what do we mean by good quality data as opposed to lower quality data. I think about these things as a tension between these two objectives. Because data doesn't exist in the universe in an IID manner. When you go grab large-scale data, you usually grab the easiest data you can get. And as you try to acquire higher and higher quality data, it becomes much more difficult to scale. Or another way to think is as you scale, you probably ending up scaling to areas that maybe that data is lower quality, or maybe it's just harder to guarantee that quality. And finally, there's this idea of constraints. Things that maybe you feel like you have to do no matter what that affects your ability to acquire data at scale as well as guarantee the quality of this data. And so constraints might be, I want to train a fully open language model where I can release the data as well. Well, that maybe makes it so that you can't necessarily scale and acquire data in certain ways. Maybe you need to pay for data, and access to paid high-quality data might be difficult for some. So think about the whole data curation strategy as basically grappling with these three ideas. Let's start with acquisition. So to acquire data, let's just take a look at where people are getting data today. Today, this is a list of known public data sets that have been used to train language models and that have been proven and validated. You'll probably see some names here. The biggest contributors of where these data sets come from is Common Crawl, Software Heritage, Internet Archive. Who are these? These seem like every single data set seems to rely on these sources. We also see some other common names appear. Archive, PubMed, Gutenberg, Wikipedia shows up a lot. There's something common about these. So let's actually break this down. Internet Archive, Common Crawl, these are web scrapers. Professionally, that's what they do. They've existed for decades. Internet Archive even since the 1996. They've been web scraping for a ton of time, and they basically provide 80% to, depending on your curation ideally, maybe 100% of your data comes from these one sources. User-provided content, so I call user as in like large amounts of people uploaded their content and then this is made available, is actually less than 1%. And this includes stuff like Wikipedia and Archive, where I consider this user-uploaded content because you uploaded your papers to Archive. This is actually a very tiny fraction of data. And what about publishers? So maybe there's PubMed, Project Gutenberg, Semantic Scholar, these organizations that maybe own a mass data, and they make their data available publicly through some sort of bulk API access. Again, very, very tiny portion. So we have a huge reliance on web scraping. What about these other sources? Well, actually, if you look over time, the same names keep popping up for a lot of recent data sets, and that's because people reuse each other's data sets. So if you're creating a data set today, you might actually just pull subsets of another past data set from the last couple of years. And finally, what about crawling data yourself? So I was looking through all these data sets that have been released, and actually very few people crawl data themselves, except for this data set from the MEP Neo team, where they crawled some amount of data themselves, but it was a very, very, very small percentage of data. So I wanted to ask this question. So we have a huge reliance on crawling. We know crawling is extremely valuable because the vast majority of data comes from crawling, but why aren't more people crawling? Let's look into this. Going back to our objectives, there's two types of crawling you want to think about. You want to think about broad, wide crawls. These are really easy to scale, so that gets you your scale. Think about your common crawls, your Internet Archives, your software heritages, or your big tech company if you have a lot of ability to do this yourself. And then you have your domain-specific crawls that gives you your quality. This is when you really, really hyper-focus on, I just want to get a bunch of math exercises from this one website, or I just want code notebooks from this one website. And that gives you your quality. Let's think about domain-specific crawls specifically. This is probably what a lot of you, if you've collected your own data before, have been doing. You pick a website, you pick a handful of websites, and you write code specific for that. This is an example of the stuff you might encounter today if you try to crawl these websites. So here's a dummy website here, and there's a little bit of JavaScript here, and if you click this button, please click the button. Look at that, it works. Text pops out. And actually a lot of websites today look like this. If you think about very valuable comment forums, the comments don't load on the page until you click next or show next comment or something like that. There's a lot of interactivity on the web today. And you need to be able to basically mess with the JavaScript, interact with the page to elicit the content from this page. And if you don't do this, then you might, when you scrape, you might only get this white stuff, like my title, click me. And you might miss the bulk of the content, like all this pink stuff that's hidden behind JavaScript. So really the takeaway is, crawling is actually kind of hard because I have to coax content out of these websites. And as websites get more and more complex over time, there's a lot more coaxing from JavaScript. And this is very site-specific. You basically pick a website, you implement logic that's specific to that website to be able to do this. Here's an example from some of our internal notes as we were considering crawling ourselves. The rows are real websites, which I've obscured what website they are. And the columns are things that we use, dimensions that we use to assess websites. And so you can see when we think about crawling websites, we think about it as, is this interesting, good quality content? But it's not just that. It's, can we even crawl this website? How much token throughput can we actually get from this website? How much coverage of the website can we even get? Because maybe the website is very complex to implement all of the JavaScript coaxing. And so maybe it's a very difficult website despite how high quality the content might be. Okay, so domain-specific crawls are just really, really hard to deal with because every single website gets its own assessment, gets its own specific implementation. Why don't we just do broad, wide crawls? Common Crawl, Internet Archive, and others do it. Well, one, this takes years and years of expertise to be able to build up because you might miss the vast majority of content if you have very simple rudimentary crawlers like the example I showed earlier. The other thing is this is a very interesting paper from Shane Longpre et al., who I think are presenting somewhere at this conference, is this idea that as AI becomes more of a public talked about topic, crawling is becoming much more difficult. Sites are implementing a lot of measures to prevent crawling. A lot more sites are opting out of crawling or indicating in some way that they don't wish to be crawled. And so the red is basically, as the red grows over time, crawling becomes much more difficult. It's much more difficult to do this yourself. So crawling overall is is in a little bit of a precarious situation. There's a lot of news articles about publishers targeting these crawlers that we depend on for our data. But if you can pay for data, then that's great. Go ahead and pay for data. And so as my colleague sitting there, Nathan has said, we aren't running out of training data, but we should think about running the consequences of running out of open training data, which we as researchers rely on. So just some things to think about. All right, let's get away from crawling and data acquisition, which is a very difficult topic, and let's assume that you have the data on your machines. So they're on your computers, they're on your servers, let's actually cook some data. How do you transform data or perform these data interventions? Well, one thing that you kind of don't really think about, but you have to start with, is this topic of linearization. Linearization is this idea that let's look on the left-hand side. Left-hand side is what a web page looks like to you. We interpret web pages in this two-dimensional manner. On the right-hand side is what this web page looks like once it's on your machine. It's just this one-dimensional linear string. And so you can see that there's some sort of correspondence between what we see and what machines see. You see the title, you see the prose, but you also see all this other stuff, which on the left-hand side, we've learned to overlook and not worry about, but this gets mixed into the training data if you use the wrong parser. Or under most parsing tools, this also shows up. And poor linearization is really consequential. You can lose points on a performance of your benchmarks by using the wrong parser. So on the left-hand side is a wet file, which is the native distribution format that Common Crawl uses to distribute its websites if you don't go to the raw HTML. And you can see it's super, super choppy. Sentences are split up. There's a lot of extra content there. This is actually the same web page. On the right is what you get if you run a different Python tool for parsing the HTML. Here's some more examples of what types of content shows up in poor parsers. Well, metadata shows up. Actually, some parsers inject extra characters. Sometimes there's a missing word, etc. This really can mess up the quality of your document. What you would really like is something very clean and interpretable. Almost on the right-hand side, you can think of it as I can read the stuff on the right-hand side, and I can derive value from it. What about not just web pages, but PDFs and other scanned documents? Oh, again, this gets even harder. On the left-hand side is a scanned document, a historical document that you might want to train on, and the right is what you get from an OCR pipeline. So OCR pipelines, you get these random symbols, you get these weird words, you get some scrambled footnotes that get interspersed in there. And actually, there's not a ton of good solutions. This is an evaluation of a whole bunch of different PDF parsing tools out there, and all of them are pretty bad, and they give you very vastly different types of content. And so you can think about what data you're training on is actually very much a function of which open source library you decided to use to process your PDF. What you would really like is you would really like something like this. No more weird symbols, proper OCR, all the characters recognized, and structured information like footnotes and whatever are represented separately. But there's also some open questions. Is there a best form of linearization, just like a ground truth that you can keep optimizing for? What about scientific papers? Where does the caption go? If it's 2 columns, we know how to read it, but where do tables go? Where does the caption of the figure go? Does it interrupt the prose? Where's the right way to put this data if you have to represent things as a one-dimensional string that reads from left to right? This is an open question. Same thing with textbooks. Look at all these diagrams, these symbols, there's some indentation. I don't know where the blue stuff is supposed to go relative to the other stuff on the right-hand side. Again, open questions as we think about when we interpret text, we interpret it in this two-dimensional format, but language models currently only see it in this 1D way. All right, now let's get into the stuff that's probably mostly familiar to people, which is filtering. We know that we have to throw out a whole bunch of data once we get it, and once we've linearized it. You throw out low-quality content. Content that might be low quality can be stuff like search result pages, aggregations. These are things that we don't necessarily have to engage with normally, but are more like aggregators that help us navigate us to the page that we actually want to engage with. So let's detect these and throw these out. There's some fun stuff on the internet that maybe we don't want to train language models on. So this is a subreddit called the Microwave Gang. where everyone just posts the letter M repeatedly, like and then people respond by posting beep. So it sounds like a microwave. Very funny, very amusing, but you probably don't need to train on this. Or undesirable content. So there's a lot of toxic content on the web, not safe for work content on the web. There's a lot of like private, very, very private information that you can find in your web crawls or in your downloaded documents. Probably you might want to filter this out. And also this idea of duplicates. How many copies of the US Constitution do you really need in your pre-training data? You can find this everywhere. So, make the most use of your tokens, train on new data. How much filtering roughly happens? So this is actually kind of interesting. Was calculating these stats when we curated the first one of our versions of our data sets, DOMA 1.7. Roughly, we had about 65-time reduction. So, and in subsequent work with DCLM folks, also turned out to be about 65 times reduction. That's not to say 65 is the magic number. This is just to give you an idea of the magnitude of amount of data that actually gets thrown away. You throw away quite a bit of data. What about all these other topics? When we think about transforming the data and data curation loop and filtering, one nice convenient thing that we found to be helpful that maybe you could use yourself is this idea that actually we should define software and we should define approaches in this common template. So we treat language filtering, quality filtering, safety filtering, all of these, even deduplication, in this common format, which we call tagging. And so let's think about tagging as basically just text classification. Let's take this tool called fast text, which is an extremely useful tool for very, very rapid text classification. Takes as text as input and produces some score at the end. Fast text classification runs extremely fast, as per the name. So roughly benchmarking, this gives you about 2,000 documents per second per CPU. For some of these instances, this can be as little as like 4 cents an hour. Whereas if you want to think about, high fidelity text classification with what's considered a small model today, like BERT base. Even BERT base, you're probably talking about 1,600 documents per second on an H100. And if based on pricing today, you might get lucky and get like one H100 for $250 an hour. There's a world of difference when you're working with these small models, small models like fast text versus something that we might even consider small today, like BERT base. And this matters if you want to process trillions and trillions of tokens, terabytes of data. Don't trust me? Why fast text? It's simple, boring models from ancient times. Actually, we all use it. DOMA uses fast text. FineWeb from Hugging Face uses fast text. DCLM uses fast text. Llama 3 paper uses fast text. These small models really do matter, and it's because of how fast and efficient they are to scale to vast amounts of data. When we think about training these fast text classifiers, text classification 101, we have to define what is positive and negative to define to train our classifier. So we can think about positive as good stuff that we want to select, and the negative as bad stuff that we want to throw out. But actually, there's two different ideologies for defining these quality classifiers. You can think about quality classifiers as, give me more stuff like this. And so if you had this ideology, you might define positive stuff as, I'm going to label a bunch of content that I think is good, using like a larger model like Llama. This is what FineWeb does. And then for negative, you might use Llama to classify some stuff that I don't think is good. And train a fast text classifier on this. So this is this pattern of distilling from a larger model into fast text and then using this to select data. Or you could think about, no, give me less like this. This still evokes this idea of quality and filtering based on quality. But if you take this ideology, you might do something like, I'm going to pull all the stuff that I think is quality and use these as my positive documents, and then randomly sample from the rest as common crawl, and that's my negative documents to train my fast text classifier. And even though these are coming from the same place, which is this idea of positive documents are good, negative documents are bad, train a text classifier to do this prediction, these different ideologies and then the little details in execution give you very different quality classifiers at the end of it. And so you select different data, your final data mix looks different. Let's think about another little tiny detail, seemingly, that actually has ramifications on filtering and tagging your documents. So I could take this document and I can label the whole document with a small model. So take this purple stuff and toss into my fasttext classifier, and I'll get some output, and hopefully this thing is tagged as good or bad quality. And I can represent this output in like so. I can think about, oh, my text classifier classifies is this English or not? And so from character 0 to 698, that's my whole document. It was English. Is it not safe for work? I can also build a text classifier for this. Is it grammatical? I could do another one for this. Is it quality? I could do another one for this. Actually, this is a very common pattern of just as long as you represent things as text classification, you can instill in your text classifiers a whole bunch of these ideas for filtering or selecting for different types of contents. So here's just some examples of different types of things that people do, all basically using either fasttext classifiers or some sort of very lightweight rules-based technique. We'll share the slides eventually also, so you don't have to take as much photos if you don't need to. But the idea here is actually I was doing this on the whole document, but text classifiers just take text as input. There's no requirement that it has to be a whole document. So what if I ran my text classifier on little chunks of the document? So maybe separated by every new line. You could run it on this, I could run it on this, I could run it on this, etc., kind of going through. And at the end, you get output that looks like this. Characters 0 to 10 is English, checked. Characters 19 to 71 is English, check, etc., etc. You could do this for your grammar checks, your not safe for work checks, your quality checks, etc. And this gives you different output than if you ran it on the full document. So basically this idea that you should think about the text unit that you're working with and not just taking this coarse view of, oh, it's just text classifiers. It's how you use text classifier actually also has significance. Duplication. I'm not going to get too much into deduplication because actually there's a lot of work at NERFs on this. Go talk to those authors. But think about deduplication as also tagging, is this idea that I can run sequentially through the document and keep tossing all of these texts, whether they're hashes or some representation, into some sort of set or data structure like a Bloom filter, and then check. And each time I see the second time something has happened, I'll flag it as, I found it. I found a duplicate. And you can keep going. In practice, a very useful type of deduplication can actually happen on the metadata of the document. So I can take that whole URL and toss it in, or maybe like a substring of that URL and toss it in and realize, oh, I've recrawled the same document multiple times. I don't need this document. And you can do this as a very coarse first stage data filter that throws out a whole bunch of data that you don't need to process. So once you have all of these tagged outputs of start, end, and then some sort of score, when you assemble your data set, you articulate some sort of logic. You basically say, I want all the documents, but I need this requirement on how English it is. I need this requirement on how many documents pass some duplication threshold or some quality threshold or whatever. And so what's recommended is to define some sort of protocol so that you can articulate this type of Boolean logic in like a configuration type manner. And so this is usually how we approach things, is we separate this idea of, oh, I don't necessarily do deduplication, I do identify duplicates, and then later I decide what to do with them. I don't do not safe for work filtering, I identify not safe for content, and then later on I decide what to do with it, etc. All right, why did I talk so much about these little details like choosing the text unit and all these things? It's because these things matter, especially for quality classification. So there's some work that looked at what do models that talk about their quality classifiers, what do those quality classifiers actually do? And so this work from Sachin Gururangan and et al. Looked at quality classifiers and looked at the documents that were considered high and low quality and noticed side effects. Things that were considered low quality tended to be stuff about high school. Stuff about campus life, clubs, sports tended to be scored as low quality. A lot of politics content, a lot of news content got scored as high quality. So quality classification, just because these models, our ability to curate these fastest classifiers, one, is limited by the capacity of these models to learn complex nuances like quality, and also our ability to articulate data what is positive example of quality, what is a negative example of quality. There's all sorts of long tail of things that we don't necessarily notice when we're developing these quality classifiers, and so we have side effects like this. There's also side effects of deduplication. So if you're running a duplicator, you're like thinking, yes, I want to remove repeat examples of documents, and so this is a useful thing that keeps my token efficiency up. Well, if you're running deduplication, and you might accidentally run into a situation where you're throwing out terms and conditions in all of your websites, because terms and conditions are repeated, they're very, very templated language that they're repeated across a lot of websites, so you might actually throw out a lot of important legal information by your documents is in the course of doing this. Again, a side effect. That wasn't necessarily your intention, but this might happen. When we think about using these fast text classifiers or using these very simple classifiers, you have to grapple with this idea of, I want something that's really fast that can scale to a lot of documents versus I want something that's high quality, that's accurate. And here's an example for a very high stakes processing operation, which is to remove private information, like social security numbers, email address, etc. And so what do you do in the case where you have a much more powerful tool like Presidio compared to using something way, way, way faster but with less fidelity, like just writing some regular expression statement. This is the trade-offs that you have to make depending on the compute that you have, depending on the time that you have, the turnaround time you have to test out different data ideas. And finally, this idea of text unit is very important because all sorts of sneaky, weird things can happen on web crawl data. So here's an example of what seems like a scientific document, but the stuff that's blacked out, I masked because it's not safe for work content in a different language. So if you toss this entire document into a language classifier, it would flag it as English. And if you only ran this whole document on not safe for work classifiers, it would say this is safe. But if you ran it at a different text unit, you would realize that there's this interspersed a bunch of ads for different types of content that you might not want to train on. All right. Finally, to end this idea around all these, what I talked about so far are these individual steps, individual patterns that you can use, but realistically, when you're curating a data source, you're composing pipelines that intersperse and interweave these different curation steps. So, and each of these, you really have to treat each different type of data source separately. So an example here is GitHub code. If you want to curate good GitHub code, you might build a language ID. But the language ID could still be a fast text classifier or it could be a rules-based thing, but maybe language means something different from code than it is for web crawl document. Maybe on GitHub code, your idea of what is quality might have something to do with, I want to check if there's doc strings. I want to check whatever, but doc strings isn't something that you're necessarily grappling with for quality. On common crawl web documents, you're dealing more with not safe for work content, toxic content on the web. Maybe your filtering techniques, you care about filtering private information in both of these different pipelines for different data sources, but on GitHub you're looking for things like keys and maybe usernames and passwords and stuff like that. For common crawl you're dealing more with like, social security numbers, people's names and addresses, etc. So think about each individual data source, how you acquired it, probably deserves its own complex pipeline, but the hope is that you can define good engineering, good software that allows you to not have to re-implement every single thing for every single news source. Finally, let's talk about experimentation before we move on to pre-training. We want to make good decisions. There's so many decisions we have to make based on what I just described once you have the data on hand. We do something which everyone does, which is called data ablations. And the idea is very, very simple. Fix your model, fix your training strategy, only change the data. If you train your model and then you see that model trained on data A is better than model trained on data B, then data A was better. This is super simple, and what we would really, really hope is that we can get away with these data ablations with much, much smaller models trained on much, much fewer tokens. So what we'd really like to see is results like this, where you can see processing in purple was a better data intervention than all these other processings because it improved the model's performance on HelloSwag very, very quickly. But of course, this is easier said than done, and this is a good tee up into pre-training because there's a lot of work that still needs to be done here. Some data interventions are really hard to test. So you can think about intuitively, deduplication is actually a really tough thing to do small, short-run experimentation on. But we know deduplication, if you run really, really long time, run trillions of tokens, you start to see the effects of. Also, small models are really, really cheap. They're really good. And sometimes you can fit these curves, which I'm sure some of you have seen, these scaling law curves on increasing small models. And as you go up in size, you're like, I can extrapolate and predict what's going to happen if I just scale to a larger model. And so I can make confident decisions that around this model class, this model style, this data style at this tiny scale. But then if as soon as you switch to a different task, you might get results that look like this instead. And you're like, I don't know what's going on then. So task-specific decisions do matter here, as in task-specific experimental configurations. To close this off, emerging threads. Just some final thoughts. Some new things that are emerging now. Data curriculum actually kind of works. What people are doing nowadays with pre-training is they're doing their full pre-training on trillions of tokens of data. But then at the very, very last stage of training, I guess people call it mid-training, some people call it end of pre-training interventions, whatever you want to call it. You can switch the data at the very, very end of training, and this has a lot of ramifications. You can build better models this way. This is the stage where you can start adding in some instruction data that maybe you didn't see, but you can still add this in before even post-training, and it still helps the model even after. You can maybe subset some of the data, start upsampling kind of the highest quality sources that you saw in stage 1, and you want to repeat them with a higher percentage, higher mixture percentage later on. Maybe drop out some of the broader web crawl data that you relied on in stage 1 just to learn basic language, but really at the end of pre-training, you really want to upsample the high quality stuff. And then think about, maybe you kicked off your training run 2 or 3 weeks ago and you don't want to restart it, but you just got some new data. That seems really good. This is probably the time to add it. And actually, we're seeing a lot of good results with synthetic data nowadays. And you can inject this near the end of training if you've curated very specially for certain types of capabilities or certain types of task operations that you want the model to be able to perform. So, final takeaways before we move on to training. What's good data? Think about scale and quality. These things can trade off each other. If you want more scale, it becomes harder to guarantee quality. If you want quality, it's hard to scale that much quality data. Data acquisition. Crawling is super hard. You need to crawl, but we also rely heavily, heavily on crawling. So please support people who do crawling and make this data public. Data transformation. Filtering is key. You need to filter a crazy amount of data, but don't forget these other processing operations such as linearization or your choice of text units when you're training these filters, because these things can have, these tiny details has ramifications on your data. And manually inspect your data often. We wouldn't have caught most of those side effects if we didn't actually just open up the file and we're like, that's weird. Good engineering really, really matters here. We exclusively rely on methods that can scale efficiently. It doesn't matter if you have a very, very powerful, the best quality filter in the world if I can't scale it to terabytes of data. And making good decisions is very much about experimenting. Intuition is very, very hard to build up here. Most things are intuitive up to a certain point, but once you want to get to the next level of high fidelity model performance, you just need to try. And so experimentation, this heavy reliance on experimentation means that you can't just develop data in a vacuum. You have to talk with your pre-training team and know all the details. So when you run an experiment and you're like, I'm sure this new data was going to work, but it didn't. Why is that? Talk to your pre-training team partners, maybe you can figure out whether maybe that data intervention didn't actually work, or maybe there's just a bug somewhere in your pre-training. All right. Break time. Until a few minutes. Good.
We'll just get started now. All right, before I start, I want to mention that we have been told that people on Zoom are not able to see the slides, so we'll just make sure to share the slides after the tutorial. So I'll be talking about pre-training. So pre-training is basically training a base language model. And the goal here is to equip the model with general language capabilities using self-supervised training. And you do this, as previously mentioned, by training on large amounts of mostly unstructured data. Just elaborating on that a little bit. By general capabilities, we mean that we measure the performance on certain standard benchmarks. The model is only trained to be good at next word prediction. And then there's no specific input or output format. So here's the way this is going to be structured. There are a lot of different technical details that go into pre-training. So things like basics of training neural networks, transformers, GPUs. So instead of focusing on the definitions and the theoretical explanations for these techniques, I'm going to talk more about the practicalities of putting them together. So I've structured this talk as follows. I'll talk a little bit about the different architecture choices that you have and some of the standard practices that current language models follow. I'll then talk about what things to look for to check the health of your run over the course of training. Next, I'll talk about how to set up experimentation and enhancing the performance with less compute. Finally, I'll talk about some engineering optimizations you can do to utilize your GPUs more effectively. And then I'll end with some takeaways. Okay, so you've decided to pre-train a language model. You have your data cleaned up and filtered from the previous step. Where do you start with the model? Historically, NLP models have processed text sequentially. So examples of this include recurrent neural networks, LSTMs. By contrast, the transformer architecture processes text in parallel. The way this works is that you tokenize your data, create an input embeddings, then pass it through several layers of what are called transformer blocks, and then through a linear layer and softmax to get a probability distribution for the next word. Each transformer block utilizes a mechanism called self-attention, which enables the model to weigh the importance of each word in a sequence relative to others. A single self-attention unit is called a head, and you can combine several of them to form a multi-head attention layer. Most pre-trained language models today belong to this category. As an aside, I also want to mention that there are other newer architecture options that people are exploring. So these are things like state-based models. In this tutorial, however, we'll be only talking about transformers. Okay, so how do you actually configure a transformer model? Here are just some of the hyperparameters and modeling configurations that you need to pick when building the model. This includes things like the size and the shape of your model, the type of embeddings you use to represent your input, and the specifics of the optimizer you use to actually train and minimize your loss function, as well as various other tweaks to stabilize and accelerate the training, such as layer norms. This is not a complete set, and moreover, these configurations can interact with each other, so the total possible combinations of all of the things you can try can be quite large. Now, you might think at this point that in the past couple of years, we have had several models out that all use a transformer architecture. Have you maybe landed on a particularly good combination of these configurations? Well, not quite. Here are some configurations that were used in recent 7B models. We definitely don't have something that can be considered the best config. And there are a lot of different choices that you can make for your model, and different teams have arrived at different decisions. We will see that some of these choices are theoretically motivated, some are empirically derived by doing ablations, and some are even made due to considerations for specific hardware implementations. That said, there are certain modeling choices that are common across them, and while these are still active areas of research, if your goal is to just build your model with minimal hassle, these are a good place to start from. Especially because picking something without running ablations can be really costly. Here, for instance, you can see how the price for training a 7B increases as you train on larger data sets. So even running ablations for a large model can add up in costs. So in this next part, I'm going to highlight some common configurations that most pre-trained models use with some variations, and these can be considered the current standard practice. But actually, before we get to configurations, let's actually ask a more basic question. Say you have a fixed compute budget. What model size do you train on, and how long do you train it for? The scaling laws literature suggests that for a given compute budget, there is an optimal model size and training tokens, and that the number of training tokens should also scale linearly with the model size. The chinchilla paper here provides some approximations, and based on these approximations, you can come up with a model size. There's also the question of determining the width and the depth of the model, and the scaling law literature suggests that the specific numbers here don't matter as much, so you have some flexibility. So as long as your model is not too narrow or too wide, you should be good to go. Although there is some work that suggests that for language models, the ratio of 100:1 is considered good. The second thing to note here is that these optimal numbers for a given compute budget are about training optimally. In practice, you might also care about faster inference. So for example, you can cut the number of training parameters in half and instead train for more number of tokens. So this is the approach that small LM models from Hugging Face took, and practically all of the pre-trained models today are trained beyond chinchilla optimality. And now let's get to some other configurations. I mentioned the attention mechanism, which is the main complexity in the transformer model. The way this works is that for each token, you have a representative vector called a query, representative vectors for other tokens called keys, and then you compute attention scores. These scores are then normalized and multiplied by value vectors to arrive at a context-aware representation for that token. This is the mechanism on the left, and this is the default attention implementation. The key and value matrix calculations can take up a lot of memory, so there are alternative variants. So the one on the right, called multi-query attention, uses the same key and value for all of the queries, and this helps with memory, but this can also degrade quality as you increase the scale of the model. The group query attention in middle uses a similar principle by having the same key and value for groups of queries, which can combine the best of both worlds. In practice, you can use multi-query attention for models up to 7B, and then consider full attention or GQA for larger models. The next common configuration is the use of rotary position embeddings or rope embeddings. As a reminder, the transformer processes text in parallel, so we need a way to encode the position of the tokens to capture sequence information. Each token embedding is represented in in rope embeddings, each token embedding is represented in a multidimensional space, and then the position information is incorporated by rotating these embeddings in each dimension based on their position. Effectively, these can capture longer sequences better. In practice, you can use a higher theta value to make models more sensitive to positional change. So Llama 3, for instance, increased the theta value from the default of 10,000 to 500,000. Moving on to the activation function. Commonly used function today is Swigloop. This is also, this combines the Swish activation function, which is easier to optimize, and gate a linear unit, which is effective at capturing long-range dependencies. Here are some other standard choices that most LLMs use. Most of them use the RMW optimizer. They all use a parametric RMS norm, and most of them follow a cosine learning schedule with warm-up. I will discuss these further in the next two sections in the context of checking the health of your run. But to summarize, the number of choices you can make is really large, and updating them is very costly. If your goal is to experiment with alternative choices, for example, if you want to develop like a new optimizer for language model training, it makes sense to experiment further there. But otherwise, you should just start with these standard choices, with the one small caveat that things change very quickly. So it's possible that this time next year, these would not be the best choices. Okay, so now you have your model architecture and you're starting to train. How do you determine that your run is training well and is going to stay stable over the course of training? You can look at the most basic thing, is the loss converging? You might have a validation set on which you're measuring perplexity to see if the model is actually learning the next token prediction well. You might even have different validation sets for different domains if your objective is to look at the model's capabilities on a particular domain like finance. You might have some downstream tasks that you care about. So most language models today, for instance, report their performance on standard benchmarks. These include things like reasoning capabilities, code, math, and so on. And these things give you a good indication of where your run is currently at, but are they enough by themselves? So consider this run. This is the in-loop accuracy for one of our older Olmo models for a particular downstream task called HelaSwag. And it seems to be improving. At 2 trillion tokens, it's actually kind of on par with other models. But will it continue to improve? So this is the plot of the norm of the total gradients for the model. As a reminder, the gradient norm is a measure of the magnitude of gradient updates during backpropagation. A large gradient norm indicates larger updates. So over the course of training, with a learning rate that's declining slowly, you would expect to see the grad norm reducing, which is not happening here. At smaller scales, you can maybe get away with this if downstream metrics at that point are all that you care about. But we want to build a model that stays stable as you continue to train, so this grad norm should still be concerning. Most importantly, as you do scale the number of parameters, the spiky grad norm can translate to spiky loss curves and ultimately cause your model to diverge. So how do you fix this? Before we get into the architectural fixes, let's actually discuss a couple different types of spikes that you can observe. So on the left here, you have a sharp increase, and then it recovers very quickly. So if you notice the x-axis, it recovers in like maybe 100 steps. In practice, we have found that these spikes often correspond to a particularly bad batch of data. So as Kyle showed, the microwave gang, that's the kind of thing that would show up as a spike here. And the solution there is more straightforward. You should look at your data, you should fix your filtering, and then you're good to go. The second type of spike on the right, it's a little bit trickier. As you can see, it builds up slowly and it does not recover. So how do we fix these slow spikes? Well, first things first, you want these spikes to happen sooner rather than later. So you should experiment with smaller models, which I'll talk more about. And you should use a higher learning rate to quickly suss out potential issues in your setup. And now let's get on to some fixes. The first thing is initialization. So literature suggests that in order to train deep neural networks in a stable way, initialization should have the following properties. The scale of the activations and the gradient should remain the same from layer to layer, and it should scale as you increase the width of your model. As a case study, I present our experience in training Olmo. Our older model from April this year performed initialization in such a way that the later layers were initialized to larger values. This type of initialization is also something that the Palm paper used, for example. Olmo 2, by contrast, uses normal initialization. We performed the analysis on activations and gradients as suggested in this paper, and we found that the older initialization did not exhibit these properties. Normal init does, so in practice you can just use normal initialization. But if you do want to experiment with init, you should at least make sure that it exhibits these properties. Let's revisit layer norms. We have already discussed that RMS norm is currently the best practice. Empirically, this has been shown to enable faster convergence by maintaining stability. Additionally, 2 other changes are helpful. The first is to apply the layer norm to the query and the key matrices. And the second is to change the order in which the layer norm is applied. So in the standard transformer, you apply the layer norm first and then the attention of the feed-forward layer. And recent literature shows that changing this order, it enhances the stability. Interestingly, in our ablations, we found that these 2 changes by themselves did not help very much. But when you use them together, they show a reduction in grad norm spikes. The next fix is to ensure that token embeddings do not become very small. And we do this by changing how we apply the weight decay. So usually weight decay is applied to every layer to ensure that the parameters do not grow too large. For token embeddings, this can actually cause the embeddings to become really small, as you can see on the left here. This is the norm of the embedding weights, and it's declining slowly if you use weight decay. This results in larger gradients in the earlier layers. And we observed that these small embeddings in our experiment and found that in practice, just turning off weight decay for embeddings worked really well. Okay, now let's talk about how best to use your compute to get good models. This is a fairly broad idea, and it can be applied in different ways. Namely, there are things you can do before you start your main pre-training run. There are things you can do after you have trained a model for trillions of tokens. And then you can use more efficient architectures. Let's dive into each of these categories. Okay, so let's first look at what you can do before the pre-training run. You can run experiments on smaller models. This may sound obvious, but there are caveats. Often the smaller model's behavior does not translate well to larger models. So what kind of experiments can you reliably run? You can find optimal hyperparameters for your main pre-training run, such as learning rate. So this work, for example, proposes an alternative way to parameterize your model weights, such that the optimal hyperparameter value remains the same as you increase the width of your model. You can also predict models. You can also use smaller models to predict the performance of your larger model on tasks that you care about. Here, for example, they use a small set of models to predict the validation loss for a 7B model, and then use that to predict the error for the average performance on downstream tasks. This can also help in data ablations, where, for example, you want to compare two different data mixtures. What about after you've already trained for a while? So there are a couple of different things to try here. The first is annealing. This is a fairly new technique, as Kyle mentioned, and language models have been using this, and it works like this. The standard practice dictates that you start your learning rate schedule with a warm-up, where you increase the learning rate to its peak value for something like maybe 10% of the schedule. Then you do a cosine decay for the majority of the rest of the schedule. And then in the annealing step, you rapidly reduce the learning rate down to 0 over a small number of tokens. There are some things here that are still open questions. For example, do you reset the optimizer state? These are still actively being discussed. In our experiments and in other literature, we have found that this gives the downstream tasks a sudden boost towards the end. So instead of completing your training slowly over a large number of tokens, you can shorten it with this accelerated schedule. You can also extend this idea further by changing the data mix for the annealing part and doing curriculum training, as also previously discussed. And this allows you to add new capabilities to your model towards the end of the training. You can also use annealing as a way to assess new data mixtures instead of training small models from scratch. And finally, instead of training dense models, you can use more efficient architectures, such as mixture of experts. Just to briefly explain what that is, if you compare the two figures on left and right, the difference between a regular dense training model is this pink part in the middle. So instead of going through a feed-forward network, in the mixture of experts architecture, you use a routing mechanism and pass the tokens through experts, and the router algorithm decides which experts to activate for which tokens. This makes MOEs significantly more efficient than dense models with a similar number of total parameters. So dense models activate all parameters for every input, and MOEs don't. Practically, we can get to similar accuracy or similar loss using less number of tokens or training flops. If you want to learn more about that, there is a workshop on Saturday that discusses this more. Okay, now let's quickly talk about some engineering improvements you can do for training your model on a distributed cluster. Concretely, the goal with these improvements is to maximize the number of tokens processed per second without losing model performance. This allows you to run more experiments faster, since it effectively increases the size of your cluster. The first thing you can use is training parallelism. Broadly speaking, this is a way of effectively distributing the computation and the data you run during training on multiple nodes and GPUs. There are multiple types of parallelism. Data parallelism splits the data across devices while keeping multiple model copies. Model parallelism divides the model weights across GPUs. Tensor parallelism splits the actual tensor, such as QKV, across GPUs, and so on. And there are things you need to keep in mind when running in the distributed setting. In practice, FSDP, or fully sharded data parallel, it maximizes throughput the best. But if you're using FSDP and scaling the number of GPUs to be, say, something like 512 or 1024, then the effective batch size also increases. So here you can add other forms of parallelism, such as tensor parallel. Another thing that you should do is to use optimizations available such as Flash Attention, which has optimized implementations for attention, and Torch Compile, which compiles the Torch modules and functions into optimized kernels. For Torch Compile, ensure that your model is implemented as simply as possible and such that there are no graph breaks. This may not be a problem because Torch Compile is constantly improving. That said, there is a document linked which is like a manual for working with Torch Compile. This is an interesting one, and this only becomes relevant with large distributed training jobs. During training, the Python garbage collector runs periodically. In the distributed setting, however, there are thousands of training processes. By default, the garbage collection does not happen on every process at the same time, and this causes more number of stalls. And you can see a noticeable increase in the average training time per step and an increase in the variability. This gets worse as the number of processes increases. So the solution here is to run garbage collection manually by triggering it at the same time on each process. This, as you can see, keeps the throughput steady and reduces variability. Another thing to keep in mind in distributed jobs, the training loop does other things besides learning model weights. For instance, it logs a lot of metrics like grad norm, for instance, and these need to be synced across devices to get computed. We also save checkpoints regularly, which can become really slow as the model size increases. The way to combat this is to use a separate CPU backend. This is how it works. The training step wants you to save checkpoints, for instance, and so it triggers this in a separate thread and then continues training in the main thread. In our experiments for the 7B model, we found that without doing this, the model was taking 2 to 3 minutes per checkpoint to save each checkpoint. And then with this asynchronous bookkeeping, the blocking time on the main training process reduced to like 6 seconds. I'm going to recommend our library Olmocore, which implements these and several other optimizations that you can apply, such as training with reduced precision. Okay, and then let's have some takeaways. First, if you're not actively researching model architectures, it's best to start with the standard practices from current literature. This is because ablations are expensive. Second, hardware-specific bugs can impact your modeling choices. For example, I mentioned RMS norm earlier as a standard practice. However, in the first version of the Olmo model, we did not use this because of a very specific bug with its implementation for AMD GPUs, which messed up checkpointing. This has since been resolved, but depending on your hardware and your timelines, you may also need to make these types of trade-offs. The third thing is throughput matters, because in case it's not clear enough by now, computer is really expensive and you should get the most out of it. And finally, data and pre-training cannot be separated into independent steps. They both impact each other. You cannot run data ablations without thinking about training dynamics and so on. I'm going to leave you with this quote from one of the papers that we discussed. We have discussed a bunch of different techniques for training large language models. A lot of these are shown to work empirically based on doing ablations, which basically treats these models and training dynamics as some type of natural phenomena that you're observing. For the field as a whole, I think it's important to have more rigorous theoretical grounding for why these things work. In practice, however, you can only ever know by trying things out. Okay, we have another break.
Get started. We're ahead of time here, but we'll shift more into Q&A at the end. So, as we said, I'm Nathan, and I'm going to talk about post-training. I think the general story for post-training is actually somewhat different, as you'll see in these slides, where data and training end up being a lot more details and just like efficiency oriented, while the story that we're seeing in post-training is evolving very quickly on just how people approach it and what the methods we're using are. So this will be kind of fun to go through. Generally, at the end of language model pre-training, we're left with these raw model weights that aren't suited particularly to any one task. They're completing text. And the role of post-training, which we call adaptation at AI2 to make it very specific to our goals, is to kind of transfer this raw pre-training into a set of downstream tasks. And most of these are classified as instructions now, but there's other things like just being generally safe and specific skills we might care about that are harder to fit into just that one like instruction following domain. So many people have seen this slide, I think, this three-stage approach, which was really popularized with the likes of InstructGPT, was where the notion of what is called reinforcement learning from human feedback was really popularized. I think after ChatGPT, we saw in the blog post that they said we trained this model using RLHF, using the same methods as InstructGPT, and most kind of educational materials on post-training were really focused on RLHF, which was this preference tuning with instruction tuning. And you can kind of summarize this in a flow chart where you have certain numbers of data points and you have certain methods, and this is what things have looked like for a while in both, at least around the time of ChatGPT, where you have some human instructions which are written to follow a set of tasks, and this gives you this instruction following model, and then you need to do something like train a reward model and do some sort of RL optimization on that in pairs of preferences to get your final aligned model. This pipeline looks fairly simple. It matches what we've seen in many academic works kind of leading up to ChatGPT. And to summarize, it was this three-stage approach where you instruction tune a model, you collect preferences, and you train a reward model, and then you fine-tune it with RL. Specifically, a lot of these papers were very focused on chat or instruction following capabilities, and the actual tasks that people are interested in for what is called post-training is much more diverse now, and it's good to have specific things that we want these language models to do so we can keep making progress. And if we shift to today, like, as I'm saying, like, it's really more complicated. So I'm going to share a few system diagrams from popular papers that kind of show how different this post-training approach can look like. And these are for static model weights. If you were to generalize to building a kind of general chat service for something like ChatGPT, there are a lot more online updates that go into monitoring user behavior and actually looking at UX questions. So this is mostly just about the actual model that we're trying to build, and you can go even further. Probably the most popular one is this Llama 3 paper, where it honestly takes a very long time to parse what is going on. You need to be using language models for multiple things, such as generating completions and filtering completions and ranking your data, maybe removing part of the human data part for preferences and using LLM as a judge, and it kind of just keeps evolving over time to get the best possible model weights. I kind of summarize this as we have a batch of tools for doing different things to the model, and I expect this to continue to grow over time. But when I think about kind of supervised fine-tuning, instruction tuning, I'll go through each of these in order, which you'll see in an outline in a second, is that supervised fine-tuning is really about building the foundation for the language model. Whereas changing it from this raw model to something that generates completions to a specific input prompt. It's still very important to improving the capabilities of models on specific tasks, but we can kind of use different loss functions for different sorts of problems. So then preference tuning, which was popularized by RLHF broadly, is really something that we're seeing to focus on like chat abilities and just what does a user like if you were to A/B test two models side by side? So like what is the best way for a user to process information? And it might not be whether or not the question is specifically right. And then we're seeing popularized by OpenAI's blog post last week what you can call reinforcement fine-tuning. And I'll have an example of how we did this later on to improve things like math or precise instruction following. So this is kind of the outline. I'm going to go in order of what you should do if you have a model and you're trying to do post-training to target specific tasks. And kind of each of these optimizations as we go on are less established in the literature. So the first part of doing post-training well is knowing what your goals are. I think if you don't have a specific evaluation you care about, is like a basic question of like, why are you doing post-training at all? And you could most likely find your data sets online. So you need to do the process of matching the evaluations you care about with prompts online. So prompts are really the guide for training the model, and your prompts should be targeted to specific evals. So what this would look like is you need to curate a set of evaluations, which might be more than you actually care about, and kind of figure out if you're trying to do a general model, which is most of the models called instruct online, or the endpoints that serve something like ChatGPT, which are targeting tens or even hundreds of downstream evaluations. There's also very specialized models. So you see math models or code models, which will be doing one subset, and they kind of tailor each of their training steps to that specific need. I think it's going to keep going in this direction, and there's also decisions like whether or not you fine-tune from an instruction model or a base model that are not fully studied in the literature. Again, so a way to think about this is you kind of can have a prompt budget to post-training where depending on the optimization stage, you can kind of put more information into the model and again, proportional to your evaluations. This is a rule of thumb which you can start with, and we see, especially in instruction tuning or SFT phase, there's plenty of open data sets that are well more than 1 million or towards 5 million prompts. I think a big thing that you should consider is how to balance this budget across different stages of training, because they all can do different things for you. Especially these last stages, we haven't seen as much of a need to scale up, because if you're doing some sort of RL training, you end up seeing the prompts multiple times throughout your training, while for SFT and preference learning, you normally do fewer epochs. So I'm going to start with this kind of foundation of supervised fine-tuning, and instruction tuning really builds this foundation. So without this stage, the models and the infrastructure wouldn't know how to kind of accept this very normal style of input that we're used to, which is something like you could ask about basic topics. So you can explain any historical topic or something you're learning about to the models. These are not natural behaviors for learning models, so we build all of this in, and it starts with instruction tuning. The actual technical detail that handles this is the chat template, which is a series of special tokens and often a system prompt that handles the user message going to the model. Especially we've seen with tool use and other types of models, these system prompts are becoming much more complicated, I think. For example, Llama's new prompt includes tools that are available in the context that the user doesn't see, or there are models behind APIs like Claude, which actually tell the model to think before generating content for the user. And all of that scaffolding for how generation is done is handled by this chat template. So it's kind of the foundation for post-training and one of the most important things that is done, and it's very simple. You can even see variation in performance on tasks based on how you handle this. But this gets us to where we can take data like this from Stack Overflow, which is a very logical example, which is like there are questions on these forums and then answers. You can take this question and then you take the continued text afterwards, and that is a kind of prompt completion pair that you can then train on. What the community has been doing extensively is building synthetic data either in the forms of prompts or completions to expand instruction data sets. And this has been seen time and time again to be successful. I think one of the nominal works is one called Self-Instruct, which is around expanding prompts and completions that came out before ChatGPT. And then this led us to a bunch of models that you're probably familiar with these names. Good instruction tuning and synthetic instruction tuning was the foundation of kind of training chat models and instruction following models in open. So these are all about a year and a half old now, and we'll get to much newer examples, but it's important to remember that while simple, instruction tuning is still very detail oriented, and you have to do a lot of data processes. So in building a good model, you kind of keep doing two things. One is you're taking existing data and mixing it together to understand how performance changes on your tasks. And if performance is not where you want it to be, you should make targeted data curation. I think one method that we use extensively is called Persona Hub, which is just a synthetic data method by Tencent AI that is for creating new prompts and getting diversity. I think you repeat doing this throughout the course of your project, and you can see instruction tuning, while simple, can still generate very strong performance. So where trends are going for this sort of data is that synthetic completions are really the gold standard. There's a small variety of tasks where human data is still needed, and that is largely where we haven't trained language models to actually solve the task yet. So as tasks like math and coding become the focus, especially for these proprietary models, there's a strong ability to distill completions from that. In many cases, you don't actually need to do extensive filtering to get performance gains when distilling from a more powerful model. But if you're really focused on specific abilities, filtering for completeness and accuracy will give more gains. So with this, we kind of have a base model that can follow instructions. And with instruction tuning, you really can do most of what is a modern post-training application. It's just whether or not you're targeting the last 10% or 1% of behavior for a really specific task. I think it's safe to say that with instruction tuning, you can still get like 80% of your performance gains in many tasks, which is why a lot of people shy away from these more complex and lesser known training methods that we're going to go into. So the role of preference fine-tuning is still something that I, having worked on this for a while, is not the easiest to articulate compared to instruction tuning and actually RL fine-tuning, because there's a lot of uncertainty whether or not argmaxing on evaluations like Chatbot Arena is changing the models to be more useful. And I still think it delivers a lot of value to the users by making information easier to process, because how you display information is deeply intertwined with the content itself. That's mostly why like certain stories and certain styles of telling stories will catch on and be more impactful. And controlling style is very important to these downstream impact of language models. And the core of preference tuning actually all comes from a RL objective that these methods are optimizing. You can see on the left half of this is a standard reward maximization objective from reinforcement learning, and it's subject to a KL distance constraint. So all of what we're trying to do is maximize the reward, whether from a reward model or some other signal, subject to not changing the base language model, the base instruction model, too much. So you can see this here. A lot of this is linked to preference literature and other history of fields that I won't go into, but we're trying to optimize the model subject to a distance constraint. And we'll see this time and time again with different optimizations. And the kind of key question is like, how do you make this reward go up without over-optimizing into kind of just kind of degradation by training too much? And that's a whole field. You can do a whole tutorial kind of on over-optimization and other RL-based training methods for transformers, but it ends up being it's not as straightforward, but that's the core of it. And the way that this started to measure this and to improve it is by training a preference or reward model. And what the reward model is doing is it takes a prompt and a chosen and rejected completion, and then it is via training increasing the probability that the chosen completion would have been preferred by the reward model. What the reward model outputs is a log prob, which represents the probability that a certain piece of text would be chosen. So mathematically, you're ended up saying that this probability is the reward in your post-training signal. And to do this, this equation here is the Bradley-Terry model, which is still very popular for doing so, which to do this, you have to binarize all your preferences again into chosen and rejected. There are other methods to do so, but honestly, it hasn't been revisited a ton in the literature, and this tends to work most for general applications. One of the most biggest stories for post-training in the last few years was asking a simple question of, can we just do gradient ascent on this without all the RL? And that is this direct preference optimization paper that you've heard about, and I know at least one of the authors is here at NeurIP, so you can track them down. And this was very impactful to post-training because it makes the infrastructure needed much more lightweight. So DPO is simpler. It uses about like 4 times less the GPU memory. It's easier to implement. You can fit the loss function here on the screen. You essentially get the probabilities of the chosen and the rejected completions in your preference pair, and then you do a loss update based on reweighting of these. And DPO is super important. So it gave us a model proliferation where we started seeing way more preference-tuned models. And it's still ongoing today, even if it feels like the rate of releases are slower. So that Llama 3 diagram I showed at the beginning, they use DPO. Tulu 3, which we recently released, we use DPO for these exact reasons, that it's easier to scale to larger teams because data mixing and just the rate of experimentation is higher. So some of the models where DPO kind of broke through was last fall, so the likes of Zephyr Beta, Tulu 2, and the big stories with these are this, like most of this, which unlocked this whole new training recipe, was through just finding a lower learning rate. Like most of why DPO wasn't adopted for about 4 to 5 months after its release in May of 2023 was that we didn't know what learning rate was best for general models. So there's a lot of things like that where it's like very obvious facts are underexplored in post-training and can make huge differences. And then this was kind of showing that, yes, it can scale to 7dB. At this point, it's been scaled to 405B by the Llama team, and I'm sure plenty more. The natural question following this is, should you be using DPO or an RL-based optimizer? And there's a lot of nuance here. There's whole papers studying this. And I've kind of reiterated the conclusion that DPO is what people use mostly due to simplicity. But if you really zoom in on your PPO implementation specific to your data set of choice, you can normally get about a 1% improvement in downstream preference tuning performance. In the big picture, you could get, I tend to say you could get about 10 times the performance improvements by just looking at your data and making data more specific to your model. I'll talk about what we call on-policy preferences in a second, and to your tasks. So making sure that you have prompts that are related to your evaluations in your preference tuning stage. So this is kind of a big question, especially for people in this room that are academics, relative to this kind of closed model API service that we've been talking about, where in frontier labs, we see extensive use of human data, especially for preferences. And you can go to a company like Scale AI, and you can buy data, and it can cost upwards of $10 to $20 per conversation, where the order of magnitude of labeling a data with an OpenAI API for preferences is less than 1 cent. So if you're going to scale this up as academics, we are all going to start with synthetic preference data. And to many extents, that works. We see labs using this for some things. Constitutional AI is an example of synthetic preference data, where they're asking for a new preference pair subject to a principal within their data set. And in the big picture, I think there's still more research to do. We know this basic picture where human data is higher noise and lower bias, and synthetic data is the opposite, but we haven't fully identified what these biases might be in the downstream models, and we still see with synthetic data substantial performance improvements, and in many cases it's even better than human data in our experiments. So this is TBD. I think the starting point for preference data in terms of pipelines and or just grabbing a data set from Hugging Face has been ultra feedback for a few years. And generally the idea here is to create a diverse set of models to generate completions for and a diverse set of prompts. So it's trying to create like a general preference data set that overlaps with your instruction base model. And it's worked for many different models, both of Zephyr and Tulu, which I mentioned, were kind of breakout models, were built on this, and ultra feedback is still used today. We use part of it in our Tulu 3 model, and we kind of replicated this pipeline. In many ways, it seems simple, as it's a very general approach. Let's get a bunch of models, a bunch of prompts, do LLM as a judge. There's specific intricacies in this work about which aspects you rate the comparisons on, but a lot of it is to be explored. Okay, from here, I would say that most of this is even more open questions, as RL fine-tuning has been kind of solidified in the last few weeks of something that people are interested in, and these slides are very cursory. And I expect this to change a lot in 6 months, where there could be very clear ways that you should and should not do this. But this is the idea of like how you can view RL fine-tuning and what it might do for your problem if you were trying to train a model. So specifically, the reinforcement learning is just another training objective where we're not worrying about human preferences. We're actually not worrying about the completion itself. So in this training, we are going to take prompts again. Prompts are kind of the core of our data. And then with each prompt for this kind of RL fine-tuning, you need an exact output, which is correct, in order to give a training objective for RL. I think there's a few examples that I highlight. OpenAI's like O1 models target large-scale RL, and we don't know a lot of details there. But within our kind of open source post-training efforts, we've used this kind of reinforcement learning with verifiable rewards idea on top of base models to actually improve performance on tasks we care about, like math, GSM-8K, and IFFL. These ideas are not really new to RL. I think part of this, some of my RL friends were like, why did you name this? And name it this because it's a very standard RL problem, which is when you get something right, you get a reward. And if you do not get it right, you don't get a reward. That's like the base RL problem. And there's a lot of work studying this for specific domains. So I've listed some on the screen for math. And the idea here is we've done a lot of post-training already. How do we target specific skills without degrading the downstream model? So I'm going to give an example of how we implemented this reinforcement learning with verifiable rewards in our Tulu 3 work, and then kind of leave most of the implementation details that we still have to figure out to future work. So the idea is we start with a standard RLHF workflow, and I'm going to kind of massage this into what a verifiable output training would look like. So in standard RLHF, you're going to have a training data set, which is prompts, and then you're going to have a reward model, which acts as your environment. And what we need to do is figure out how we can do this in kind of a constrained setting. So if you expand the RLHF agent, you'll see that within RLHF you have many copies of models. You have the policy that you're generating from and updating. You have a reference policy with frozen weights. And you have a value model independent to this reward model that's the environment. And the question is, how do we change the reward model to target very specific prompts and behaviors? So in our work, we first tried adding a reward to the reward model if the completion was correct. And this is kind of logical, which is saying we should be able to interweave rewards. We know that we can check if a math question was right. And it ended up being that because the fine-tuning was so focused, we actually didn't need to use the reward model at all. So the reward from the environment is just checking if the answer is correct. And in order to warm start the model, we used a value function that was initialized from an actual trained set of weights, which was our instruction model. And then what you do with this is it really is as simple as, well, simple. You have to implement distributed PPO training still, but you generate from the model, you have a Python function check if the answer was correct, and then you give the policy update a reward if the answer is correct. And this is something that we've seen specific gains on the 3 domains we've tried, and the formulation can be generalized to other things like code, and then there are ideas if you can try to use a general verifier for domains that are a little bit more open-ended, and in OpenAI gave multiple examples in their blog post where the data looks exactly like the format we're structuring here. And the big innovation to kind of make this RL fine-tuning a mainstay in post-training recipes is that we're able to implement this across a wide variety of base models. So we've tried implementing this from both instruction models and preference-tuned models, and you could see that if the model has not yet saturated an evaluation, you can normally gain performance. And you should think about this as how do you distribute training across multiple stages, knowing that you can target different evaluations at different times. So I'm going to kind of wrap up this adaptation section with just a list of open questions for things that we've seen, whether they're seen in industry and we don't know how to reproduce them, or that they're just fundamental issues to scaling post-training for the next few years. One of the methods that we've seen mentioned a lot across kind of large-scale research, but not in a lot of academic venues like this, is substantive studies of rejection sampling, which is the idea of weighting your supervised fine-tuning samples for instruction tuning with the reward model. Similarly is the fundamentals of how to actually train a reward model. In the last year, we've seen multiple evaluations for reward models come up based on either classifying tasks, which is like basic behaviors like do the reward models know basic facts correctly, versus correlating with style evals. So a reward model should be able to rank a model better that actually performs better on Chatbot Arena. These are questions we're studying, but there's a lot of research on how to actually train a reward model that is useful for a wide variety of tasks and not just chat performance. This is one that I mentioned earlier, is how do we disambiguate the signal and the noise in preference labels. I think answering whether or not human data is crucial to academic and open post-training is essential, because we need to know whether or not we need to be mobilizing as a community to build these data sets, because most individual institutions will not be able to spend millions of dollars on human data. And finally, there's a big difference between academic research, which is focused on evaluations, and this kind of closed API and ChatGPT-like research, where they're focused on this user interfaces. I think, for example, Claude is known to have a very specific style, and we have to understand if this is an important problem to academic research and how to study it. From here, I'm going to just kind of zoom way out. So this is the end of the post-training section, and we're just going to kind of recap, like, what do we need to do to actually build these open language models? The start of this talk was all about building foundational knowledge for how to approach language model research while these technologies are changing substantially. And the core of this is that research is still needed, and that can be only done in the open. Some examples that the community is interested in are here, and this is all to say that we need to continue these. And a core theme of this talk is that there have been tons of details that you need to keep track of in order to do this. So to do research, especially at this scale, with the amount of details and complexity that we're managing, you have to stand on the shoulders of past research, and that is a lot of how we've done this to build the knowledge that we have in this tutorial. We have some images on the slide, and we've compiled a list of resources that you can access online, which is what we call kind of Friends of Open Source Language Models and Friends of OLMO, which is really focused on places to find and create data and places to use training code where you can kind of like actually do this yourself and not just rely on weights or APIs that are out there. If you have questions, a ton of people contributed to this work. This is kind of a random ordering and collection of them, but you can please get in touch with us. We're going to shift into a Q&A now, so I'm going to summon Kyle and Akshita back. And we also have a demo if you're interested in playing with these models, and I put the link to the resources up again. Are these on? If you come up to the aisle microphones, we'll kind of alternate slides and do Q&A for the remaining time.
Hi, hello. This is a little bit of a side question because it's on multimodal large language models like MOLMO, which is amazing. Thank you, thank you, thank you. Post-training seems to be largely instruction tuning. It kind of follows the lava recipe. You just pre-train a model, and then you do supervised fine-tuning with instruction data. And I'm curious, like, why there hasn't been this elaborate post-training recipe for multimodal models like there are for text-only LLMs.
I think it's just early. I think a big story of MOLMO is like by focusing on the base data for multimodal, which is a fine tune, they were able to get incredible performance. And as performance is harder to gain in tasks they care about, they will add more optimization stages.
Cool, thanks.
Hi, yeah, so my question was, it seems in the last year, the line between pre-training and post-training has become a lot more blurry. Like now people pre-train on FLAN and instruction tuning datasets, or they use all of these extensive filters that try to maximize downstream benchmark performance at pre-training time. So how can, like, are base models now better than they were a year ago? Or are we simply training more task data and thus the evaluations just seem better? This is my question. And how can we make sure that we keep track of how much we're actually improving and how much are we just shifting, the burden to earlier stages of the pipeline?
Yeah, good question. I think there's a lot of what you're asking that's still open. I would say for now, it's a little bit of both. So I do think base models are getting better. And we can kind of see this with higher quality data. With new releases of high quality data, same base model pre-train on it, even without doing this sort of mid-training stage, you are just getting better performance on downstream tasks. So there's clearly better improvements. As you improve stability and training of these training runs, you are resultingly seeing 1-2 points higher across benchmarks. So base models are definitely getting better. The blurring is happening because it works and because it isn't necessarily cannibalizing on downstream. This is a hypothesis, like maybe there is a world in which we've optimized this mid-training phase way too much and it starts hurting, but I would say that this is active investigation that we're looking into.
Thanks.
Yeah.
What do you think are the most promising approaches for decreasing bias in synthetic data and specifically getting to a point where synthetic data gives us out of distribution responses for training future models to ensure that the flywheel isn't just the snake eating its own tail?
You want to do it for post-training first?
Yeah, I think you'd address this differently at multiple stages. I gave a shout out to this Persona Hub paper because it was surprisingly effective at letting us scale our synthetic instruction. So the focus of this paper is they created personalities. So like, I am a forester and I'm working X, and then you ask a language model to create a prompt specific to that personality. And then we would train on those prompts and synthetic completions. And I was like, I include it specifically because I'm so impressed by how simple it is and to the extent it improved our performance. I think like example would be like we would be gaining 1 to 4 points on math eval with other known open data sets, like Numina math was one from former colleagues of mine. But then we like did this persona math and it just gives us like 10 points. And it's just, I think a lot of it is going to be in what is a research question. But then probably a lot of the ideas that end up winning out, as we see again and again, are ones that are scalable and end up being simpler. I think in pre-training, there's a bit of different meaning for what synthetic data is. I don't know if you want to talk about rewriting.
Yeah, so with pre-training, I would say that I don't necessarily like the term synthetic data because I think that it's this idea that we're using machinery, software to generate data, and that's always been true. If you're looking at pre-training data, even before these LMs, when you're curating pre-training data, you have to throw out a lot of data that's already synthetic generated out on the web. Think about like how many web pages on Yahoo, like stock marketplace exist. It's just basically some auto-generated pages around like that's auto-populating these numbers from some spreadsheet somewhere, and you get tons and tons of these pages. Synthetic, you always have to catch that this is happening, define filters for throwing these things out, and experiment whether this helps to keep or actually you want to throw it out. And I think nowadays it's just the tech is a lot more powerful, so you generate a lot more fluent thing, but this is the core pattern of, I've realized that this exists in my pre-training corpus. I should identify it and then ablate its presence is something that has always existed. And so for me, it's just a try empirically, and probably what we'll see is some types of synthetic data is good, some type of it is bad, and it's a lot more nuanced than just the catch-all of synthetic.
Thanks.
Hi, thank you for the tutorial. Quick question. If when you're trying to fine-tune a model, you typically have two options. You can start from fine-tuning the base model or from fine-tuning the instruct model. For example, from llama base or llama instruct. Which one, in your opinion, is better, or how would you choose between the two?
It really depends on your level of investment. I think you could put ballpark numbers on it, but it's like our post-training effort was about 20 people and a substantial amount of synthetic data. So if you don't have a specific budget, like a big enough budget, you should fine-tune from instruct. And also, if it's a very narrow domain of tasks, I think a lot of it is like you want to start from the strongest foundation that you can, so you don't need to reinvent the wheel. I think if you have data provenance concerns or like they train on something you don't want, you also is a reason why you need to start from a base model that you know. But I generally think because like it's just a different research focuses on fine-tuning for base because it is a clear research problem. But if you're doing applications, I don't think that is what you should like you should try both.
Thank you.
Unless your domain is like wildly different from the current instruction tuned models.
Thank you.
Oh, thanks for the talk. I have a question about pre-processing. You mentioned that it matters how you pre-process different types of data, like PDF files, for example, or HTML. So I'm specifically interested in, let's say, academic publications on archive. PDF files that contain figures and citations and things like that. Do you know any maybe state-of-the-art practical methods of dealing with pre-processing publications that are on archive, like scientific publications?
So we'll definitely share like some resources for like tooling. I know we promised that, so we'll share this. Off the top of my head, right? Look out for some stuff in a couple months, maybe a few months. I know Lucas is like, yeah. Look out for some stuff that we'll release. But for the most part, There's a couple of tools that I think we can attach to our slides. Like Git repos, basically just using fast RCNNs to train on color sort of perturbs LaTeX documents that basically do figure detection and stuff like that. But really the key thing here is not detecting figures. I think we're pretty good at that. The key thing here is compiled PDFs. PDFs don't store reading order, so they actually just store every single glyph and its XY position on the page, and then PDF parsers interpret that reading order. So what you end up getting is like 2-column papers, like a lot of old Nearest papers. They actually read left to right across the page, and that's just like an absolutely chaotic type thing. So that requires just more sophisticated models that are still being developed or soon to be released.
Thank you.
No, thanks for all your work. Really appreciate it. I wanted to explore your thoughts on going beyond the preference tuning paradigm. So, for instance, I don't know. I wonder if the sort of verify step-by-step sort of paradigm is enough to take us all the way to sort of very high-level reasoning structures that sort of go from granular to very high level, and sort of wanted to get your general thoughts on that.
I think generally we've seen in the past few months that learning from verification is a very important thing, and we've been given advice that output verification is the most powerful signal. I think we implemented this and it worked, and I think that a lot of that again is to complexity. I think getting per step process data is complicated, and we don't even know. Like the core question is knowing if you need it to do something like these O1 reasoning models. But I do think that's kind of a core theme of the talk, is that like there's this kind of middle layer where fewer people might end up doing it because it is so general. I think we had a question on fine-tuning from instruct models, and I think a lot of that effort is getting a very specific style of chat that users like, and many people might not need that. So you might need a simple model that follows instructions, or you might need tasks that are very specific and you want to get very high performance on those. And then, as you said, it is kind of like a middle layer where it makes sense that fewer applications may use preference tuning. But in order to completely understand the process of building one of these models, preference tuning will not go away anytime soon because it is incredibly important.
Okay, thanks.
Hello, thank you for a wonderful talk. I had a question if you ever ran into a problem where there was just low resource training, where you just don't have enough data for a specific task you're fine-tuning for. And if you found any ways to adapt and not have to get more synthetic data or go back to and gather more data, and maybe go about, and how would you go about it if you saw anything like that?
So on the pre-training side, I think this data curriculum idea has quite a few legs. It's a newer-ish idea, but fundamentally, you can see how this idea that you can do late-stage data interventions in very long pre-training runs, and it helps a lot. Helps in the case when you don't have a lot of data. Like if you want to be economical with the data and you know that data is high value, maybe add it to the end. So that's one way you can think about this. In terms of augmenting data that's low resource, I think of it as just going back to some language modeling 101 ideas of match to your target domain using just continue going through common crawl, find the subsets of common crawl that match the target type of data you want, and put that at the end of pre-training. That's sort of your domain matching data search strategy. If you want more data that looks task-specific, like instruction tuning data, I think there's plenty of examples of synthetic workflows that work out there. Mishmash a bunch of this structured data as well as unstructured data added in the end of pre-training. That stuff tends to work.
Thank you.
Thanks for the talk. I have another question about fine-tuning. So recently there have been an increasing body of works on gradient-free methods where you sort of use a small amount of data and then based on heuristics directly added the model's weights. So this could be editing the memory of the large language model, or just some specific behaviors to make the model more prone to refuse to give an answer, or maybe less prone to refuse. So I'm wondering if you've got any experience in this area, and more importantly, what you think about the prospects of these methods. Could they potentially achieve what people use RLHF and preference fine-tuning for?
I don't see any reason why not. I think a lot of these methods are popular because you're more accessible with fewer resources, if you can, like a LoRa or other related things. And by that reason, because more people are using them, there will probably be ways that they succeed. And then a trend, especially like what we talk about in pre-training and all these things, is that the ways to get absolute performance is often through scaling and types of things. So I think that it's kind of a yes, and we'll do both of these things. And I mean, we even see people, I mean, you see like if we ever get Apple Intelligence, like that is what they're talking about doing, is like these small weights that get swapped. So I think there's a spectrum, and you choose your approach based on your kind of cost structure and the performance needs that you have.
Right, thank you.
Thank you for the talk and open source contributions. I have a question about the effect that instruction tuning has on models' knowledge acquired in pre-training. It seems to be the case that, taking MMLU as a canonical example, that instruction-tuned versions of many of these models outperform the base model. And I've even found this with Olmo. But in the slides, we're talking about how maybe instruction tuning largely is focusing on like formatting. And I've even found this to be the case in pretty like underrepresented domains like virology, where I don't think these would be pretty common in like instruction tuning. What's your thinking on how these maybe knowledge benchmarks improve when you do kind of instruction tuning or chat tuning?
This is something we've spent a bunch of time on and don't have a conclusive answer. I think what we expect from conversations and other literature is that you need to do kind of document recall during fine-tuning, or build questions based on documents that are closely matched to your tasks of interest, which is kind of to keep letting the model see these distributions that you care about. I think MMLU is the one that everyone talks about. You can look at the subtasks in MMLU and like where your model is degrading. And it's like someone needs to build this in the open, which is like just like a model MMLU degradation tracker or improvements. I think it's extremely detail oriented. You have to do a lot of careful data curation and make sure all of your multiple choice questions are correct in the right format. The basic things are like adding questions of the same format, which we've tried and didn't really give performance boosts. So it is really about like figuring out how to integrate knowledge, but I don't have a clear answer because we haven't figured it out.
Fascinating. Thank you.
Thank you for the talk. In the post-training, if we are developing a domain-specific model and the experts have answered for something which is not there in the pre-training data, that means the experts have a knowledge base of like a question that they came up with an answer, but it's not there in the pre-training data. What we are seeing is that it doesn't get reflected very well when in the final inference, because the data, the input data was spotty, but though the expert had an answer for that, which was provided in the post-training, it was not necessarily manifested in the inference. Have you seen similar?
We haven't worked on these domains, but I would zoom out and say that this is why data store language models are exciting, because this is a fundamental language modeling problem that you have some information that you want to have exactly in context, but you may not be able to train on it, and or your model may forget it during training, which is why like there might be more types of architectures used for different tasks in the future.
Thank you.
Yeah, thank you for the talk. It's really interesting. So I have a question about the role of value models in PPO, or, I mean, in your post-training pipeline, maybe you dispense with the value models altogether, so I don't really know. But if you do use value models, have you found like that they are actually good at the task they're trying to do? Do we have progress to make on value models? Because like the Vine PPO paper suggests that actually having good estimates of value speeds up your training by a lot. Yeah. Your thoughts on this?
You mostly summarized it. I think you could see by like our approach of, oh, let's just try this, and we use a different initialization, and then it works better. It's very new, and Vine PPO is a paper like we've been discussing with the authors and trying to understand how our settings are related. So I think that this is just like we need to know. I think from looking at preference models, I don't think that the value models will be as correlated as you might expect. So there's like the value model will be compared to a preference model because it's trained explicitly on the output signal, but there's a lot of basic interpretability, and like we're saying we're training preferences, but it often becomes weirder if you zoom into it.
Okay, thank you.
Hi, thank you for the amazing session. I just had a specific question around the pre-training part. So you mentioned that that you use garbage collection, and if you don't use it, you see a lot of performance variability. So, I mean, from what I understand, like when you train generally using PyTorch, there's automatic garbage collection like that's built in. So, are you saying that does not work as well, and you have to do it manually?
Yeah, so basically the way the automatic garbage collection works is that every different process is going to run it at a different time. And so you're going to stall every single process at different times, and so that adds up as the number of processes increases. So to mitigate that, it's better if you run all of them at the same time, and so you're reducing the number of stalls.
Oh, okay. Thank you.
Yeah.
Hi, so you mentioned how important data quality is for the model performance, and I wanted to ask you, so assuming the model performs better on data A than data B, how do we actually know that it performs better? And even if we use data C for evaluation, how do we know it is not just that data C is more similar to data A? And if there are other ways of dealing with this bias than just online evaluation, which can be hard to do in certain setups?
Can you explain, clarify the question a bit more? What do you mean by bias in the case of data A, B, and C?
Sure. So, like, how do we know the model performs better on this data if for evaluation we mostly also use the data? So it could be the case that we are just matching, the data that is used for evaluation and not the actual performance.
We try to address this by having truly unseen evals that are in similar domains and see if we generalize to evals that we are not specifically targeting during development. But I think the generalization is one of the most important abilities that we try to look for. And Kyle, you can say more.
No, I think this is very much a question about generalization and what level of generalization are you expecting or hoping for. I remember when BERT came out and the discourse around this was, well, is it even generalizing because you're just training on the whole internet? You're crawling everything. And people were like, no, it's fine, because even though it sees test time X, it doesn't see test time Y. And that's okay, that's tolerable generalization. We have sort of different notions now because we're dealing with autoregressive models, but every era of tech, you're always dealing with this idea of what is a level of generalization that we expect. I should train a model and never see any Wikipedia articles ever and have it be able to do tasks on the Wikipedia articles. Most people probably don't have that opinion of like, no, we should train on Wikipedia. But then you're just working with a different definition of what type of generalization you're working with. I should have never seen any math or even just basic low-level math, and I should be able to do slightly more complex math as a result of it. Again, you're seeking a different generalization problem. So I think right now, just sort of when we do research, you just got to be clear about what you're hoping for, and then not every single research project will have the same definition generalization that you're hoping for.
Thanks a lot.
Hi, thank you for the great tutorial and for coming here and answering our questions. My question is a bit specific on data for both pre-training and post-training. I'm wondering, how do you find the best signal to noise for both pre-training and post-training? I know this is a bit of a hard thing to like grok out, but yeah, like how do you choose which data is the most important for your model, and how do you separate that between pre and post-training?
Take that. Yeah, go for it. Oh, okay. Sure. Pre-training is tough. Pre-training is tough fundamentally because you're always working with very small models that are undertrained, way less than what you would actually want at the end of your hero run. I would say this is still active area of research, but fundamentally the thinking right now is every single task, there's a minimum amount of model size or flops input into this task before which the model starts doing something beyond random. And discovery of what this is key, because if you're under that amount of computational effort put into this model, or if under some sort of model size capacity to be able to measure, then there is no signal, it's just noise. So that's at least first step. From there, I would say everything is in terms of, can you define an experimental procedure that has that's sort of climbing up this increasing model size, increasing length of training run type of thing. So what we do is we do things like, okay, let's train small models to 1x chinchilla, 2x chinchilla, 5x chinchilla multipliers and see if we can continue extrapolating and the trends in my experimental setup still holds. For the same model size to longer training runs. If it does, then I feel more confident that there's some signal here when I make decisions. Same thing with model size based extrapolation. So extrapolate along these two dimensions and the hope is that if everything seems to hold and the curves look clean and there's not a lot of noise and you rerun the whole procedure with new randomly sampled data and you see the same trends hold, you feel pretty good. But
I want to give a specific example of like the types of tasks that you evaluate on. So for example, with the scaling laws stuff that Kyle just described, certain tasks, like formatted differently, they're going to behave differently at different scales. So for example, the same task, Hella Swag, if you format it as a rank classification format, smaller models are going to pick it up much faster. If you are using a multiple choice format where the output is only the choice A, B, or C, smaller models are going to have a hard time picking up that task. And so in that case, you may want to include a larger model as you're trying to make predictions for even larger models.
Okay, thank you so much.
I will add for post-training before the next question is that this is something that would be good to put in the next iteration of slides is that most evaluation for post-training should be moved to generative tasks where you're generating tokens. And most of the time the models you're using are like, there's way less of this noise concern. I think you can calculate whatever your base like evaluation noise is on a static checkpoint or on like a basic training run, but it'll end up being much easier to disambiguate signal from noise once you just train on a specific data set and see if you get performance, and then the mixing is looking to see if you lose performance by mixing two data sets normally, and that is just it's a very different problem than what they were discussing.
Great, thank you.
Thank you so much for being here in your talk. Regarding post-training again, so if you have data, you want to improve the models for a specific task, have you ever looked into in-context learning if you're not able to do, say, robust fine-tuning or robust pre-training?
We haven't done a ton of it in our research area that is mostly limited due to personnel. I would expect that it can work. I think there's some papers that I can think of, or you come after, I can find one of them that's like the seminal work. But I think in some of my friends in the area, I feel like it's just like a chronically underexplored thing because it's either like less scientific or just less flashy. And it's one of these, like I would do it at the end. It's like the size of the intervention you just do later in the process. And it's worth trying as a quick thing for applications.
Okay, great. Thank you. Appreciate it.
Hello. My everyday work and research is more connected to representation learning of language models. And my question is, now that we have this new paradigm with RL, reinforcement learning, do you see any way that representation learning can benefit from it? Or not really? And the second question, general, how do you see representation learning in face of LLMs?
Do either of you know a lot about language model representation? I think we're largely not experts in representation learning. I can give an anecdote that like the RL loss function is very different. So right now we're doing mostly small scale training where if you measure the KL distance of the model, the actual change of the model is almost negligible, but the performance gains can be quite big on tasks that you care about. So you can get like a 5% improvement on math, which is one of the flagship evaluations right now, where the KL distance, if you compare it to preference tuning, is like 1/20th or 1/50th of the distance, or even about 0. So that points to me of saying like there is something changing in this representation of the model. You can see the behavior change as it does chain of thought, but I don't know the terminology of the field to do this.
Okay, thank you.
Yeah, thanks for the talk. When generating data, synthetic data for SFT or preference fine-tuning, we might often use chain of thought. You know, we'll say, first explain in detail your reasoning, et cetera, then output the code or the whatever. Is there any guidance around including that including those reasoning chunks in the data for preference fine-tuning or for SFT and the effect of one or the other?
It's common practice to include them, especially as a lot of evaluation. It's like your evaluation, you determine your suite. I think at AI2 we try to determine like general evaluation suites, which are not too specific. If you look at like a Llama math eval, they'll have a specific prompt with it. But I think in general, especially post-training, a lot of these evaluations are chain of thought, and you need to do this in the model. I think for math data, most of the prompts will be like solve this step by step, or it's deeply intertwined. Like you could get a number for like the percentage of data points, but it's probably going to be like it's not going to be a small number.
Yeah, thanks.
Yeah, thank you for your talk. I have a question about pre-training. So some papers suggest that to train a model, we should use 4 million tokens per step.
Say that again, please.
Some papers suggest that to train a large language model, for example, Llama 7 billion, we need to train with 4 million per step, 4 million tokens per step. So as an expert, could you provide what is the best practice for determining the number of tokens per step during training based on the model size?
Yeah, so there's some literature that I can link to later on, which basically develops scaling laws for things like batch size, which is essentially the number of tokens you see per step, and things like learning rate. So there is literature available that you can use as a starting point.
Thank you. Talk about determining like model size based on hardware, because that's the other thing is like I don't know.
Yeah, I mean, so the thing with model size is that there is some leeway. In practice, you basically want to use the largest possible model that you can fit on your hardware, and then within that, you make a few tweaks based on batch size and so on.
Yeah, then we need to compare our model for our training curves with actually, for example, Llama 7 billion.
Yeah.
Then for fair comparison, we should feed the same number of tokens, to the model, because they should see this. They should train with the same information.
Yeah, I mean, scientifically, I agree with you. It's just that because the hardware is so different, even if you're using NVIDIA GPUs, depending on the cluster, the model training dynamics are going to change a lot. So it's really difficult to actually have a fair comparison, and you can't really ablate on all of those different choices, and minor things can have a bigger impact. Yeah, I think aiming for the ballpark is the best that we can do right now.
Okay, thank you.
Hey, thanks for the awesome tutorial. My question is centered around data ablations and effectively reducing the cost of data ablations, because Kyle, you mentioned it's quite expensive to do that. And so I think one way you already mentioned is like extrapolating that from smaller scale data ablations. My question is, essentially, what are the training-free ablations or like factors you can look at that reliably can predict? So I personally work on multimodal models, and in CLIP, for example, you can look at sort of train-test overlap and frequency of concepts in the training data set to sort of get a rough, reliable trend of how downstream performance will scale. I'm just curious, A, what are certain relevant factors there? And B, how reliable are they if you don't want to do data ablations?
This is, what was A again? So I couldn't quite hear.
A is how reliable are those factors, and like what are those factors first of all in language models, and how reliable are they?
For setting up an experiment, what are the factors? I think it's probably related to an earlier answer. One, the task itself, how it's formatted, like Akshita said, the level of intrinsic noise and ability to move that metric is probably the number one biggest factor. So much of our experimental setup is just because we tried something, it works on HelloSwag, and then as soon as we switch to a different downstream task, you're like, this doesn't work at all. We have to do a completely different setup because we can't see anything. So study your task, understand what moves it, what is it actually testing? Is it testing knowledge retrieval, or is it testing multiple choice format following? Like, what is it actually doing? What's the level of intrinsic noise? How sensitive that benchmark is to different changes to your model or your data. That's number one. The second factor, I guess, do you want to talk about, I don't know, do you want to talk about small model setups or scale model setups?
Yeah, I mean, even with small model setups, I think the general idea is that you need to have evaluations in a way that they give you signal for what your end goal is. So for example, for our research, because we are comparing against a lot of these other language models, there are some standard benchmarks. So there are things, MMLU is something that we care about a lot. But that may not necessarily be the case if you're doing something for a specific domain. So I would really start by setting up your evaluation in a way that is more useful for your end goal.
And I think maybe there's a little bit of a weird thing, but at the end is once you've sort of determined that this is the benchmark, this is the format, this is the evaluation, at some point you just have to trust it and just optimize that benchmark really hard. Because you can't keep, I think oftentimes with language model development, one of the biggest bottlenecks in activity is just getting stuck on, I ran this thing, it didn't work. Is it because my benchmark is bad? Or is it because it didn't actually work? And you can't get stuck forever in that mode. At some point, you kind of just have to decide to trust it and then leave cleaning up, doing a new benchmark to like a later time.
Awesome. Thanks.
Hi, thanks for the great talk. I have a question about the reinforced learning on verifiable rewards. So you assign positive reward on the correct answers, but I found you didn't apply a penalty, a negative reward on the incorrect answers. So I'm wondering why you didn't apply it, because for DPO it's actually encouraging the correct ones and penalizing the incorrect ones. So I'm wondering why it still performs better than DPO. Yeah, that's my question.
I think the comparison to DPO is kind of like apples to oranges, where the DPO loss function is just for this kind of chosen rejected thing. And then if you view this RLVR just from pure RL angle, I think the kind of value shaping is a very classic RL problem, where if you look at the like what PPO or one of these optimizers is doing, it's like the value function gets transformed into an advantage, and there's an implementation detail where you end up whitening this distribution to be unit normal anyways. So whether or not you have a negative for a wrong answer ends up being normalized into the learning process. I think in this case, we have an implementation where if your model doesn't generate an EOS token, it gets an even bigger penalty. So that's actually incorporated into this loss function, where it's like the model knows that it needs to actually finish its thought as well, which in this case is to getting to an answer. But most of it is just kind of absorbed into the RL optimizer. And in DPO's case, that optimizer doesn't exist.
Thank you.
Hi, I want to ask about tokenizers, because I think it wasn't mentioned on the talk.
Okay.
Is that a good or a bad question?
No, go for it. Go for it. We might call in a consult, but go for it.
Okay, yeah. So, I mean, yeah, it wasn't the talk, and I think a lot of people just ignore tokenizers. But you do I mean, that kind of makes sense if you don't do pre-training, but you do pre-training, right? So yes. I'm curious to know if you have tried things that just failed, or if you think that it doesn't really matter, and because I think it kind of matters also, like vocab size impacts obviously the training efficiency and inference as well, but there's also BP versus Unigram. Do you want to use that chorus regex from GPT-2 or not, and stuff like that?
Tokenizers definitely it depends on who you talk to on our team, but tokenizers are either very important, so you should definitely work on them because there's literature on this around scaling the size of your vocab with the size of your model. It seems like this is generally true. You can think about maybe doing digit splitting, and that has empirical consequences. I think we even have some results from this morning that it's like, oh, it actually improves some benchmarks if you actually do some proper fixes in tokenization. You can also talk to other people, which is tokenization is a trap. Don't work on tokenization. Just pick a good tokenizer and then optimize everything else. I think tokenizers are a realm of interesting research since it's contentious.
Okay. Thank you.
Hello.
Oh, you can go.
Yeah, thank you for the talk. I just had a few questions. So the first one is with regards to the stage 2 training. So with regards to stage 2 training, how do you all decide on like a 100B token budget? And also, how do you decide which data to be put into stage 2 training? And my second question is a bit more towards for the data ablational studies, we look at, and also the tracking of pre-training models, we look at like the validation loss, and we also want to see what are the impacts on the downstream performance. Yeah, so I was just curious if we could get a bit more details into how we choose some of these downstream metrics to look at. Because just now you mentioned MMLU, but for small model scales, usually the model performance is closer to random.
So I can answer the second part. So we do observe that MMLU performance is random for very small models. So we ran experiments at the scale of 190M models to 1B models. Again, formatting is really important. So if you're trying to evaluate in the MC format, 1B models don't really do well on MML. You need to go to at least 7B. So if you just want to get some early signal, might want to try formatting your task a little bit easier. So for example, rank classification. So in that task, we do see that once you start getting beyond 500 million parameter models, MMLU does start to show some signal.
I think in our case, it's like you experiment. You asked about token budget, and in this case, we try multiple things in experimentation, and if you get the same performance at a sixth of the tokens, like you just go with the smaller one. Yeah. So we've tried more tokens, and it was not noticeably bigger, but in a later model, it might be that we have a better mixture of data, and then we need to use more tokens, and it's very new.
Yeah, I think the overarching takeaway here is that you need to try a bunch of things and see what works.
Okay, thank you.
Hi. Thanks for the talk first. So I have a question about the reasoning. So people are recently more focused about, many people are more focused about the reasoning ability of the LM. So especially after like 01 Pro is out. So we've seen some very tremendous reasoning outcome. But we also see like some 01 Pro, they might fall or fail in some IMO difficult problems. So my question is, so in your experiments for SFT, pre-training, fine-tuning, and also post-training parts, I saw, especially in our tuning part, you used the outcome-supervised model, the raw model, which is mostly outcome-supervised to train the generation model. So I was wondering whether you have also tried using PRM, like process-supervised raw model as well, and if yes, then how do we actually measure the reasoning ability of the language model? So do we really need to look at the reasoning processes, or we can just directly look at the outcome of the LM in some reasoning tasks like GSM math problems or some maybe high school math problems? And also how good the PRM is actually helping for the language model to gain this general reasoning ability. And also, if we really care about the reasoning ability, how do we monitor this throughout all of the trainings, like pre-training, SFT, and post-training?
Okay, there's many questions in here. I think that's the question is like, what does what we presented mean in the context of reasoning? And I think the biggest kind of debate right now in reasoning is whether or not reasoning is a general skill or if these methods are just tuning to specific evaluations. And we don't know what O1 models exactly are doing yet, but I would guess on most of it being based on this kind of outcome verification, or that is the foundation of it, and then figuring out how to train models that achieve this. And it's generally, like PRMs I mentioned earlier, is just a much higher complexity solution to approach this, but it doesn't mean that it won't work, and it largely needs to be resourced. Do we want to call it?
Is 12?
Yeah.
Yeah.
I think we might wrap up and head to lunch. I personally will still be around. It's just a change in venue and kind of make sure people know that they can move on and go to the next thing. But thanks for the great questions.
Thank you.